and then write a computable expression that gives the values exactly. So then apply the fundamental theorem in order. So we want to interpret the expression, but then we want to have a way to get its value, and that's through the fundamental theorem, right? Through the fundamental theorem, we interpret that, and then we can write it in a different way. That's what we said, right? There's a different way to write that that's computable, and then solve that or simplify if appropriate. So whatever's appropriate, simplify to have an exact expression. So the first one, explain the meaning of that thing. Explain the meaning of that thing. Is it a function? Is it an expression of x? Is it a value? What is it? First of all. I hope we know that by now. So what is it? It's a value. It's a number. That whole thing represents a value, a number. And we want to be specific. What value or number is it? What value or number is it? Anyone want to give it a shot? Yeah. No. The meaning. What is that? The meaning of that expression? Yeah. Okay, it's the amount of change. It's the amount of change of some quantity. All right? It's the amount of change of some quantity. That's the first part. What else? Yeah. Okay, from x, so it's x changes from 1 to 2. It's an amount of change of some quantity as x changes from 1 to 2, and then there's one more thing. What's that? With a rate of change of x to the fourth. You see? That whole thing expresses a value that's an amount of change of some quantity whose rate of change is x to the fourth, and it's the amount of change as x changes from 1 to 2. We're going to be looking at integrals all semester, and so this is how you have to interpret those. Okay? And so if it's the amount of change of some quantity, so it's the amount of change of some quantity as x changes from 1 to 2 when the rate of change is x to the fourth. And by the fundamental theorem, we know that's the same as the amount function, what, taken at 2 minus the amount function at 1. There's another way to express that amount of change. There's another way to express that amount of change. If we had the amount function, all we would need to do is do the amount function at 2 minus the amount function at 1. And that would also give us the amount of change for this quantity. How are x to the fourth and capital F related? How are those two functions related? What is capital F related to x to the fourth? If x to the fourth is the rate of change of capital F, then capital F is the antiderivative. The antiderivative. So just like the name sounds, antiderivative, we're thinking of what function has that as its derivative. So what function has x to the fourth as its derivative? Okay, so we think about what function, if we took the derivative of it, would we get power 4? Well, it would be something with power 5, right, by the power rule. But what about x to the fifth? Does that give us a derivative x to the fourth? No. It gives us 5x to the fourth. We don't have a 5. Therefore, if we have a 1/5 there, it'll take care of it. So 1/5 x to the fifth is the antiderivative of x to the fourth. That's like our amount function. So we're going to evaluate that at 2. So this is our f of x. Our antiderivative is 1/5 x to the fifth. We can evaluate that at 2. Evaluate that at 1. And look, so we're calculating the total change. The total change in this amount as you change from 1 to 2. Whatever that turns out to be. 32 fifths minus 1/5. 31 fifths? Did I do the math right? That's where I sometimes make mistakes. So if I ever make a mistake, you guys are becoming mathematicians, right? This is calculus 2. So I encourage you to tell me that I've made a mistake. What was it? 2x. Right? So if I ever make a mistake, you're going to tell me that I've made a mistake, right? You're not going to sit there and go, well, he's really smart, so he must be right. Remember this? What happened? Not one Calculus 2 student out of 150 students told me this was wrong. And this is pre-algebra. So I'm counting on you to catch my mistakes. All right? Yes, I'm a math genius, but I'm going to make mistakes, okay? And I need you to catch these, okay? All right. So now you've got some more practice to do here. I want you to do these three. Same three things. Explain the meaning of each expression. Do that first. Practice this. Practice this. It's going to be repetitive, but we got to practice it. So what was the first one? It was the total amount of change of some quantity as x changed from 1 to 2 with a rate of change of x to the 4th. Practice that on these other ones, okay? And then you're going to use the fundamental theorem to write a computable expression and then solve or simplify that as much as you can, okay? But we want an exact result, So get a partner, do these three together. It's going to just be 5 minutes because we got something else to do. Just 5 minutes. Go. Practice explaining the meaning. So verbally, get a partner. You're verbally talking out the meaning of each one. Okay, so I'm gonna skip right to the last one. So I want to hear a couple people, somebody new, interpret the meaning of that. Interpret the meaning of that. Someone who we've not heard from before, who would like to volunteer. Don't be shy. Yes, sir. He says the total amount of change as x goes from 10 to 35 at a rate of change of 2x times square root of x squared plus 3. Yes? How do you do? Yeah, that was perfect, right? That's perfect. So this is the total amount of change of some quantity, we don't know what it is, whose rate of change is 2x times radical x squared plus 3 as x changes from 10 to 35. The amount of change as x changes from 10 to 35, okay? So, and to get a computable expression, it's going to be the final amount, g of 35, I'll call it g this time, g of 10. And what is capital G? What is this function capital G that's going to allow us to compute this total amount of change? The antiderivative of our rate function, right? The antiderivative of our rate function. So we have to really know our derivatives. So this is a harder one. We have to really know our derivatives here. So we think, what kind of derivative ends up looking like that? Notice that I've got x squared plus 3 here, and then what do I have here? I have 2x out there. What kind of derivative ends up looking like that? Do you remember what it's called? Should. The chain rule, right? The chain rule. The chain rule, you had a composite function, and when you took the derivative of it, you had the derivative of that thing, and then times the derivative of the inside part, right? Isn't this what this is? We got the derivative of the interior function right there. So if we were going backwards, in general, what would the initial structure of that function be? So really this is like 2x times x squared plus 3 to the 1/2. So we're thinking, what function would have a derivative that looks something like that? Anybody? X squared plus 3 and 2/3, right? Okay. So this is kind of like a guess. It's like a guess. How can we check it? Find the derivative. If you find the derivative of that, and you get exactly what you started with, then we got the right antiderivative, right? So you got to know your derivatives. So knowing antiderivatives is a matter of just knowing derivatives really well. That's the way we want to approach it. We just want to know our derivatives really well, and then so well that we could do them backwards and in our sleep. Okay? So derivative of this is, so now we're going to check. Derivative is what? 3/2 times 2/3 times, this is chain rule now, so we leave the interior as it is, remember? Power rule, am I done? Chain rule says now times the derivative of the inside part, or the interior, which is that exactly what we started with? It is. Therefore, conclusion, that's the right antiderivative. And so how do we now compute that? We're going to do, that's our antiderivative. That's the capital G function. Plug in 35, plug in 10, and subtract. So it's going to be 2/3, 35 squared, plus 3 to the 3/2, minus 2/3, 10 squared, plus 3 to the 3/2. And we could go further, but that's trivial. So this is, we have the value now. We have the value. Okay, so we're gonna work hard. We're gonna formalize this in a moment here and work hard on these, because these are the kind of the most common, harder antiderivatives that we'll have. Okay, It's based on the chain rule, but it's the chain rule in reverse, right? It's the chain rule in reverse. Any questions before we move on that example? Yes. Where did the x go?
Yeah, so you went from 2x, x squared plus 3 and then 2 over 3.
Because when you do the chain rule, you start with a composite function, and then the derivative has two things multiplied together. So if you're going to reverse it, it's going to collapse back into 1, right? If you reverse it, it's going to collapse back in. And we just checked it. So we did the derivative of our attempt and saw that it was exactly the same. So check. Got it. Other questions on this example? Okay, let's generalize it. We're going to call this undoing the chain rule. We're going to call this undoing the chain rule. What does the chain rule say? It says that you have a composite function, g of f of x. How do you take the derivative? You look at which function first? The exterior, right? You do the derivative of the exterior with respect to the interior. And then here's the chain part. Then you chain on the derivative of the interior. So you all got through Calc 1, you got through your mastery test, you had lots of chain rule problems. This should be very familiar. And then you had some practice for today's homework. Okay? So if we're doing this as an antiderivative, we're looking for something of this form, right? We're on the lookout for something that has this form that is like the result of chain rule. And the antiderivative is we're gonna put it back together to its original g of f of x. So then what will you focus on in the rate of change function, right? That's the rate of change function, our derivative. What will you focus on there in order to recover the amount function? What are you gonna focus on? You're gonna focus on g prime of f, or are you gonna focus on the part that would be like f prime, if we're trying to recover this g of f of x? Naturally, what are you going to look at to get g of f of x? Which one? The first or the second factor? The first. It's almost the same thing, right? Look, it's so close. I don't have to do that. I've got it all set up to do that. Okay, so that is, it's like one thing away from the answer. How do you compare that to that? What are you going to do to that first part to get the antiderivative? There's one thing to do, basically, which is what? Are you going to look at the exterior or the interior? What changes? The exterior. All you have to do is worry about the exterior function and do what to the exterior function? Antiderivative. And you're like 95% there. Then there's maybe a little mess to clean up. So if you can find that part of the rate of change function, all you need to do then is figure out what the exterior function is and do the antiderivative, and you're basically done. You're almost done. So what will the approach be? We're going to write the antiderivative of the exterior function g prime, keeping the interior function f as is. That's the approach. That's it. So that's going to be the way that. So we're always on the lookout for. We have an integral, and we know that's the rate of change function. We're on the lookout for. Oh, this is the result of a chain rule. This is the result of a chain rule, and we're going to apply this. We're going to focus in on which part is the composite part, the g prime f, and then really all we have to do is do the antiderivative of g. And we basically we a little bit more to do, but that's it. All right, so this says the same thing as we said at the last slide. So here's an example. So I've got x cubed times 8 plus x to the 4th, all to the 5th. So we're going to think of it like this. We're going to think of this as like g prime f of x times f prime of x, the result of a chain rule, and we need to recover the original g of f of x. So where's our focus going to be? Is our focus going to be on exhibit A or exhibit B? Exhibit A or exhibit B? B. B is like the g prime f. And how can we check that? Well, if that's right, then this is like f prime, right? This is like the derivative of the inside. Is it essentially the derivative of what's inside here? The power is right? So it's just off by a factor of 4. The derivative of what's inside there, a plus x to the 4th, if it's like our f prime is essentially x cubed. It's 4x cubed, but we can handle factors no problem, right? So what are we going to do? So we're gonna make a stab at it, right? So if this is our g prime of f, then what's our attempt going to be? Our attempt is going to be like g of f, right? That's what we're trying to recover, the original function. So, anyone think you can, what is our first attempt going to be? We're just going to focus on the exterior function, leaving the interior as it is, and do the antiderivative. Yes, sir?
Could I like take a plus x to the 4th and like set it equal to say?
No, it's going to stay the same. It's going to stay the same, right?
Right, but could I like say that a plus x to the 4th is like u, and then
Okay, so
like u substitution?
yeah, I'm giving you an alternative that I believe is better. I'm trying to give you it, but if you want to, so the rest of the calculus world is going to learn something called u substitution. We're going to do that a little bit later, but what I'm trying to show you is it's not something new. It's based on what you already know, the chain rule. And if you get good at this, you can do these problems 3 times faster than using u substitution. So I'm trying to give you something that I believe is better, okay? But the whole rest of the calculus world is going to pull you towards u substitution. They're going to pull you that way. But try to trust me just for a week and see, and then if you don't like it, then go learn to u substitution, okay? All right, so what am I going to do? I'm looking for the exterior function, and I just need to do the antiderivative. What's the exterior function? Something to the 5th. What's the antiderivative of something to the 5th? The same thing to the 6th. In fact, 1/6, right? 1/6 to the 6th. Okay, now we're almost done. We almost got it. All we have to do now is we're going to check it. How can we check it? Find the derivative. So we'll do a first attempt. We're going to find the derivative, and then we're going to compare. And then if it's a little bit different, then we'll make a second attempt based on that difference, and then we'll be done. Okay? So we're going to check it. The derivative is to the 5th times what? 4x cubed. Now we look at that, and we compare it to what we started with. Is it exactly the same? No. How is it off? By what factor? It's off by 4. So how do we adjust the first attempt so that 4 won't be there? How do we adjust the first attempt so the 4 is gone? What do we? 1/4. We need an additional, another factor of 1/4, and we'll have it. So second attempt. 1/4 times 1/6. 8 plus x to the 4th to the 6th. If you're still not 100% confident, do the check. When you do the check, you should get exactly, your derivative should be exactly the function we started with. Okay, and then you could combine, you can multiply. All right, and since this is an indefinite integral, we need the plus c. You learned that in Calc 1. So why this way? Because once you get good, first of all, if you're not really learning something new, it's based on something you already know, the chain rule, and when you get good at it, you'll be able to do these problems a lot faster than u substitution. Okay? You'll begin just to see it. You can see it, and you can basically write it down. You don't have to go through all that method. Okay. Okay, so homework will be, part of the homework will be your revise and get your quiz as best you can. And then there'll be more on Blackboard, so just keep, look at Blackboard for the assignment, and I'll see you Wednesday. Have a safe break. Have fun.